So we'll think more about electric fields and electric potentials and how they are related. So just a reminder of a few things. That there's a relationship between electric potential and electric potential energy. And remember how it always works. This is created by some charge or charges. A new charge comes into the same neighborhood as the charges that caused this. And now that that new charge interacts with the old charges that were already there, now you've got some potential energy that you didn't have before. And then here's our relationship between electric field and electric force, a little bit similar in that this is, you get electric field caused by a bunch of charges, and when a new charge comes into that region of space, it feels the electric field caused by the old charges, and as a result it feels a force. And one thing that you've seen in both the readings and in the assignments, one feature of electric field is that it always points from higher electric potential towards lower electric potential. Let's think about another relationship between field and potential. Just imagine a situation like this. You've got some charged object that moves from here to here, just experiences some displacement that we'll call d, and it starts from rest, and when it gets to the final location, it stops there. So the final velocity and the initial velocity are both 0. And to keep it simple, we'll just say it moves along a straight line, and it feels some kind of a force, an electric force, caused by an electric field. And that force will point either same direction as the direction of motion or opposite to the direction of motion. And of course, while this thing is moving and feeling a force, that means work is done. Here's our rule for work. And if that electric force points to the right, in other words, same direction as the displacement, then this angle, which is the angle between displacement and force, is 0 because force points to the right, displacement points to the right. There's 0 degrees of difference between those two directions. And then cosine of 0 degrees is +1. If the electric force points to the left, it's pointing 180 degrees opposite to the displacement. So leftward force with a rightward displacement. The angle between force and displacement is 180 degrees. Cosine of 180 degrees is -1. So in the two situations that we're looking at here, cosine is either plus or -1. So if we consider only the magnitude of the work, then the magnitude of this term is just plain 1. And then the magnitude of work is just the magnitude of the force times magnitude of the displacement. And in that case, the magnitude of the displacement is just distance between the start and the finish. And to save ourselves a little bit of writing, we'll just call that distance plain old d. So that's what we've got. Okay, now let's consider a case where this force is an external force. It comes from somewhere outside the system. And so there's work done by an external force, and so that work done by the external force changes the energy of the system. the numerical value of work done tells you by how much the energy changes. But of course, within that system, the energy change can show up as a change in kinetic energy and or a change in potential energy. And the kind of potential energy that we've got now is electric potential energy. But remember, in this case, the object started with zero velocity and ended with zero velocity. So its initial kinetic energy is zero and its final kinetic energy is zero. So the difference between initial kinetic energy and final kinetic energy is zero. There's no change in kinetic energy between the start and the finish. That's zero. So in that case, the work done shows up entirely as a change in the system's electrical potential energy. So then the magnitude of the work done will just equal the magnitude of the change in electrical potential energy. Let's write out these two sides in detail. Well, magnitude of the work, that's just force times d. And then magnitude of the change in potential energy is, change in potential energy is just charge times change in voltage, right? An object with this much charge moves from some point with one value of potential to some other point with a different value of potential, and then this is just the difference between the final and initial values of potential. Okay, the absolute value or magnitude of this is just magnitude of charge times magnitude of the potential difference. Remember, this is an electric force, so we know that it must be equal to charge times field strength times d. All right, now we've got what we were looking for. There's a factor of magnitude of charge on both sides of the equation, so we cancel that out. On the right here is just magnitude of field times d. Here's magnitude of the potential difference between the starting and finishing point. So divide both sides by d. Divide this side by d, and all we've got left is magnitude of the field. And divide this by d, and we've got magnitude or size of the potential difference divided by the distance between the 2 points that have that potential difference. So there is a relationship between electric field strength and the amount of potential difference that you have between any 2 points d meters apart. Well, this tells us several things. It tells us if you get a lot of potential change over a very short distance, lots of potential change over a small distance, that implies a strong electric field. And any charged particle then that comes into that region of space will feel a strong force. And then look at it the other way around. If you have just very little change in potential over a large distance, that implies a weak electric field. And in the extreme case, if you have no potential difference at all, as the potential difference between one point and another point is no difference at all, they're at the same potential, then that is zero, and you get no electric field whatsoever. So you need potential difference to have electric field, or you need potential difference to have electric force, because you need electric field to have electric force. Lots of change in potential between one point and another gives us a strong force. Very little change gives us a weak force. No change gives us no field or force. So there's one way of illustrating this with by thinking about equipotential surfaces. Equipotential surface just means a set of points in space that are all at the same potential, just like the name implies, equal potential. And then usually in our drawings we have just equipotential lines. That is where the plane of the blackboard or the paper that we're writing on intersects an equipotential surface, and then that intersection is just a line. So here are some equipotential lines. We have electric field lines, remember that also. We always use a solid line to represent electric field lines, dash line to represent equipotential lines. All right, so the way we usually draw equipotential lines is that when you go from one to the next, that always corresponds to the same amount of potential change. Like say if the potential changes by 10 volts when you go from this line to this line, then the potential changes by 10 volts when you go from this line to this line. And the potential changes by 10 volts when you go from this line to this line. So for example, let's say the potential of this line is 50 volts and the potential of this line is 40 volts, and then the potential of this line is 30 volts, and then here's 20 volts and 10 volts and 0 volts. Well, one thing we know is that we already know electric field points in a direction of decreasing potential. So electric field is always going to point this way, more or less to the right, because more or less to the right means decreasing potential in this diagram. And specifically, if I say draw some arrows to represent the electric field vector at various points, here you travel a small distance to get a 10 volt potential change. So D is small for our 10 volt potential change, and a smaller D means a stronger field. So I'll draw a longer arrow to indicate a stronger field. And then the spacing around here is the same as it is here. So here you go the same distance to get a 10 volt change. Here you go the same distance to get a 10 volt change. So 10 volts over the same distance the field is the same at both those points. Now, out here, you have to travel a bigger distance to get that same 10 volt potential change. So, same value for this as before, but now this is larger. You have to go farther to get the same amount of potential change. Bigger denominator means a smaller fraction, a weaker field. And so we indicate that with a shorter arrow. Vectors with smaller magnitude we always represent with shorter arrows. Okay. Now, one thing to notice here, these fields are roughly in this drawing perpendicular to the equipotential lines. Let's make that a little more clear on this one. And that's always the case. That besides knowing that electric field always points from higher towards lower potential, and knowing that the magnitude, the strength of the electric field depends on how far you have to go to get any particular amount of potential change. The third thing we know is that electric field must be perpendicular to an equipotential line or an equipotential surface. And it's not too difficult to understand why. Let's imagine the situation that we would have if fields were not perpendicular to equipotential lines. So here's an equipotential line, and imagine the electric field points that way. Well, we can think of two components of that electric field. There's a component of electric field right along or parallel to the equipotential line, so we'll call that E parallel. And then there's a component of E perpendicular to the equipotential line, pointing that way. So we'll call it E perpendicular. And the actual electric field is just the sum of those two components. E parallel plus E perpendicular. But now, you've got some electric field pointing this way. Electric field always points from higher towards lower potential. So if there's an electric field pointing this way, that means a point over here must be at a higher potential than a point over here. But that cannot happen because this is an equipotential line. The potential here is the same as the potential here because it's an equipotential line. And when potential does not change, you don't have electric field. Just say that again. Here's our rule. When the potential is the same at 2 points d meters apart, well, if the potential is the same, then of course the difference in potential between those 2 points is 0. And the difference in potential between any pair of points on an equipotential line is 0. That's what it means to be equipotential. They're all the same potential. So if there's no difference in potential, there's no field. Moving along the equipotential line, you don't ever see any change in potential. So there's never any electric field along this direction, meaning there can only be electric field along the perpendicular direction. So electric field always perpendicular to equipotential. One more example just to see how that works. Let's here, say we've got some equipotential lines here. Now they get a little closer together. And now they get closer still. Okay, and let's say the direction of decreasing potential is, let's again say this way. So here's say 100 volts and 90 and 80 volts and 70 and 60 volts and 50 and 40 volts and 30 and 20 volts. All right, what would electric field lines look like? Well, electric field is always perpendicular to equipotential lines. So out here, where the equipotential lines are all vertical, that means the field lines have to be horizontal. Like that. And the flow of the field lines is from left to right, because towards the right is the direction of decreasing potential. Now, all of a sudden, the distance you have to go to get a 10-volt change in potential is smaller than it was before. So this is still 10 volts, this is smaller, so electric field is stronger. Wherever electric field is stronger, you can indicate that by having electric field lines that are closer together. So something like this. All right, there must be some region of space where there's a little a little curve in the electric field line, but then wherever I've actually drawn an equipotential line, the field must be perpendicular to that equipotential line. And then here, now the spacing between 10-volt potential changes is even smaller. This is still 10 volts and this is even smaller, which means electric field is even stronger. And a stronger electric field means you have to draw the field lines even closer together to indicate that even stronger field. So same thing as before. You'd have a picture looking sort of like that. All right. So one other thing I wanted to just look at for a second. Let's say you've got here some negatively charged particle, and over here you've got a positively charged particle that's moving, passes by this negatively charged one. Makes some kind of a path like that. Right. It's attracted by this opposite charge, so it comes closer and closer, but it's moving fast enough, it's got enough momentum that it'll still be able to move away from the negatively charged particle. And we'll consider a simple case where this has a much bigger mass than this. So for any particular amount of force, this will have a much smaller acceleration than this, small enough that we can take the acceleration of this to be essentially zero, which means a constant velocity. And then we imagine looking at this situation from a reference frame in which that constant velocity is zero. Right? Imagine that we're just sitting on this negative charge. From our perspective, in that reference frame, it looks like we're not moving and this big charge is not moving, and it looks like the positive charge is just passing by like this. All right, imagine 2 points along that path, call them X and Y. Right? Y is closer to the negative charge, x is. Okay, first, remember, think of the way we think about it. Before the positive charge gets close to the negative charge, this negative charge has still created electric field and electric potential in all the space around it. And what do we know about that electric potential caused by just one lump of charge? Here's the rule for electric potential caused by just one lump of charge. That K constant times the charge divided by however far away you are. Since this charge that's causing there to be potential all around here is negative, that means the electric potential is negative at any distance, no matter what distance you are away from the negative charge. As this particle moves from x to y, it gets closer to the negative charge, so this number decreases. So moving from x to y implies that d decreases. That is, the denominator here gets smaller and smaller. So that means the absolute value of this fraction gets bigger and bigger. Remember, this is negative. So what that means is that this negative number stays constant. This gets smaller. So this becomes a negative number with larger and larger absolute value, or a more and more negative number. When D is big, this might be, say, 1 volt. And when D is negative 1 volt. And then D gets a little smaller, and so this gets a bigger absolute value, and then the potential is negative 2 volts. And then this gets a little smaller as the positive particle keeps on getting closer, and so then the absolute value of this increases from 2 to 3 because the denominator is getting smaller. But it's negative, so the actual value goes from negative 2 to negative 3. And then really close, D gets really small, so the absolute value of this gets really big, but the actual number here is negative. So you might have gone from out here, the potential might have had an absolute value of 3 and an actual value of negative 3, and then here an absolute value of 10, but an actual value of negative 10. So as D decreases, in other words, as this particle gets closer and closer to here, it sees more and more negative potentials. The potential gets more and more negative as you get closer. Becoming more and more negative really means decreasing, because of course to get from one negative number to an even more negative number, you have to subtract. Right? -1 and then subtract 9 gives you the even more negative number. So the potential is decreasing. Or the change in potential is negative. The potential is getting more and more negative as you get closer to this charge, or as this positive charge moves from x to y. Okay, now what about potential energy? Potential energy is just charge times potential, or change in potential energy is just charge times change in potential. Remember, these potentials are created by the charge that is already there, and then you get potential energy when a new charge, this thing, gets close enough to feel those potentials that were created by this, and that way it interacts with this. I'm already calling this charge plane Q, so I'll have to give this charge a different name. I'll call it Q prime. So Q prime is positive. Just figured out that this is negative. So positive times a negative is a negative number. The change in electrical potential energy is a negative change. The electric potential energy decreases. And to be specific, it gets more negative. Okay. Now, we're trying to simplify things as much as we can, and a good simplification that's actually quite reasonable in most electrical cases is to assume that this system is isolated. No external forces that can do any work, and when no external forces do work, energy does not change. So here's a system of two particles, the positive and the negative, with constant total energy. Constant total energy means no change, but the actual change in the total energy could be a combination of some change in kinetic and some change in elastic potential energy. We already figured out that this was negative. So if these two things have to add up to 0, this must be positive. That is, the electric potential energy decreases by some number of joules, which means the kinetic energy has to increase by the same number of joules in order to keep the total energy unchanged. So kinetic energy increases. That means this particle is speeding up, which is exactly what you would expect, because the particle is moving more or less towards the negative charge, and since this is opposite type of charge from this is feeling an attracting force from this. So this is feeling a force pulling the positive charge more or less this way, while this charge is moving more or less this way. So velocity and force point in the same direction, and we know from 2201, whenever force and velocity point the same way, the object is going to speed up. All right, now you can try a few things.